There's an object out there in the dark, moving through our solar system right now, and every 16.16 hours it breathes. Not spins, not tumbles, breathes. Like something with a pulse, exhaling 25,000 kilometers of gas into space with the precision of a metronome. The math says it's impossible for a rock. The physics says comets don't work this way, and yet 3I Atlas keeps pulsing, keeps firing jets in directions that shouldn't make sense, keeps defying every model we throw at it. Avi Loeb thinks he knows why, and there's a test that could settle this and prove whether we're seeing nature or something else entirely. Stick around, because what we're about to uncover might rewrite the rules. If you're as captivated by this cosmic puzzle as I am, go ahead and subscribe so you catch every update as this story develops. Leave a comment telling me where you're watching from, what hour it is in your corner of the world, and whether you think we're being told everything about what's really happening out there with 3I Atlas. Part 1. The Pulse Discovered. The 16.16-hour shockwave and what it breaks. Picture this. You're an astronomer in the summer of 2025 scanning data from an interstellar visitor that just wandered into our solar system. You expect the usual stuff, maybe some rotation, a bit of wobble, the kind of gentle variation you'd see from a tumbling space rock catching sunlight at different angles. Instead, you find something that makes you double-check your instruments. Every 16.16 hours, like clockwork, this object blazes brighter by tens of %, then dims again. Not a gentle fade, a pulse, a rhythm so precise, so powerful, that it looks less like a rock spinning and more like something breathing. This is 3I Atlas, and it's currently scrambling every assumption we've made about how interstellar objects behave. The discovery of this regular pulse came into sharp focus on July 1st, 2025, when observers started piecing together continuous photometry of this visitor. What they found wasn't just unusual, it was mathematically impossible under the standard comet model. We're talking about brightness swings that shouldn't exist if this thing is just a frozen chunk of ice and rock doing lazy barrel rolls through space. Let me ground you in what we're dealing with. 3I Atlas is moving fast, interstellar speeds that mark it as a visitor from beyond our solar system, joining the ranks of the only other confirmed interstellar objects we've detected. 1I/Oumuamua, which confused us back in 2017 with its weird acceleration, and 2I/Borisov, which at least had the courtesy to look like a normal comet. This new visitor seemed ordinary at first. Observers assumed they were watching simple rotation. You know the model, elongated nucleus, shaped like a potato or a football, turning end over end. When it shows its broadside to us, it reflects more sunlight and looks brighter. When it's edge-on, dimmer, simple geometry. Except it's not simple at all once you do the math. Here's where things break down. Recent imaging from the Hubble Space Telescope, sharp enough to put actual numbers on this thing, showed that the nucleus, the solid core of 3I Atlas, is tiny. We're talking an upper limit of about 2.8 kilometers in radius. That's small. Really small when you consider what dominates the light we're seeing. Most of the brightness doesn't come from the nucleus itself. It comes from the coma, that vast cloud of gas and dust surrounding the nucleus, glowing and scattering sunlight across hundreds of thousands of kilometers. Now, run the numbers. If the nucleus is that small, it contributes less than 1% of the total light. Less than 1%. So when the entire object, coma and all, brightens and dims by tens of % every 16.16 hours, you've got a problem. A rotating nucleus can't explain that. Even if you stretched it into the most extreme elongated shape imaginable, even if it were a perfect mirror tumbling through space, the change in reflected light from the nucleus alone would be a few % at most. Nowhere near the massive swings we're observing. This is where Avi Loeb enters the story with a radical rethink. Loeb, a Harvard astrophysicist who's no stranger to controversial ideas about interstellar visitors, looked at the data and proposed something that sounds almost biological. He suggested that 3I Atlas isn't just spinning, it's pulsing. It's ejecting gas and dust in rhythmic bursts, inflating and collapsing its coma like a cosmic lung. Every 16.16 hours, this object breathes. It pumps out material that expands the coma, making it bright. Then the material disperses or fades, and the object dims again. A heartbeat. Not a rotation, a heartbeat. Think about what that means. If Loeb is right, we're not watching passive reflection of sunlight off a tumbling rock. We're watching active, periodic outgassing on a scale that changes the scattering cross-section of the entire coma. This is dynamic behavior. This is an object doing something, not just being something. And if the standard comet model can't explain it, if rotation fails mathematically, then we're forced to ask what kind of mechanism could drive such a regular powerful pulse. The stakes here are bigger than one weird object. If 3i ATLAS is genuinely pulsing, if its brightness variations come from rhythmic ejections rather than simple geometry, then our canonical understanding of what interstellar visitors look like, how they behave, and what drives their activity needs serious revision. We've only detected a handful of these travellers. If even one of them doesn't fit the mould, it cracks the mould wide open. And here's the thing that should keep you up at night. We have this pulse. We have the data showing it repeats with eerie precision. We have the mathematical proof that rotation can't explain it. But we don't yet have the full picture of what's actually happening during each pulse. We don't have the smoking gun time-lapse that shows the comet expanding, the jets firing, the whole cycle playing out in real time with timestamps and solar geometry overlaid. That data might exist somewhere, locked in proprietary archives or still being analysed. Or maybe no one's captured it yet. Either way, we're standing at the edge of a mystery with one foot over the line. So let's dig into why rotation fails. Not just conceptually, but numerically, why the math simply doesn't work for the potato-shaped rock hypothesis. Part 2. Why rotation fails, the numerical impossibility, not just the conceptual one. The rotating potato model is elegant in its simplicity. You've got an elongated object, think of a football or an oblong asteroid spinning on its axis. As it rotates, the cross-sectional area facing Earth changes. Broadside, maximum, area, maximum reflected light, maximum brightness. Edge on, minimal area, dimmer. This is Astronomy 101. It's how we've explained brightness variations in asteroids and comets for decades. It works beautifully for most objects, but 3i ATLAS isn't most objects. Let's start with what we know from the best imaging available. On July 21st, 2025, the Hubble Space Telescope captured its sharpest look yet at 3i ATLAS. What it showed was a diffuse, glowing coma with no resolved nucleus. The solid core of this thing was too small to appear as a distinct point of light even under Hubble's gaze. From that non-detection, astronomers could set an upper limit on the nucleus size, about 2.8 kilometers in radius. Could be smaller, but definitely not bigger. Now, let's do some basic geometry. The surface area of a sphere is 4 pr squared. For a 2.8 kilometer radius nucleus, you're looking at a surface area of roughly 250 square kilometers. That sounds big until you compare it to the coma. The coma, this vast cloud of gas and dust, scatters sunlight across an effective area measured in millions of square kilometers. The nucleus is a grain of sand in a spotlight. Even if you assume the nucleus is perfectly reflective, a flawless mirror catching every photon, its contribution to the total brightness is a rounding error. Here's the problem. 3i ATLAS varies in brightness by tens of percent. Let's be conservative and say 20%. That means the total light output changes by a factor of 1.2 every 16.16 hours. If only 1% of the light comes from the nucleus, then even if the nucleus went from maximum reflectivity to complete darkness, an impossible scenario, you'd only get a 1% change in total brightness. Not 20%, not even close. You could argue, well, maybe the nucleus is extremely elongated. Maybe it's not a sphere, but a long, thin rod. Fine, let's stretch it. Make it 10:1 aspect ratio, wildly elongated. When it's broadside, you see 10 times the cross-section compared to edge-on. In theory, that could give you a brightness ratio of 10:1 from the nucleus alone. Except, remember, the nucleus only accounts for 1% of the light. 10 times 1% is still just 10% of the total brightness, and that's assuming perfect conditions and perfect geometry. We're observing 20 to 30% swings or more. The math doesn't close. It's not even close to closing. This is what I mean by numerical impossibility. It's not a matter of tweaking parameters or assuming slightly different albedos. The deficit is fundamental. The nucleus is too small, and the coma is too dominant. If brightness is varying this much, the variation must come from changes in the coma itself, not from changes in how we view a static nucleus. So, what changes the coma? In a traditional comet, the coma is relatively stable, over short timescales. Sure, it grows as the comet approaches the sun and sublimation ramps up. It shrinks as the comet recedes. but those are slow, gradual changes tied to solar distance. They don't flip-flop every 16 hours. For the coma to brighten and dim so dramatically and so regularly, you need a mechanism that periodically dumps fresh gas and dust into the coma, then lets it disperse or fade. You need pulsation, you need activity. Random sublimation won't cut it. If jets were firing sporadically in random directions, you might get noise in the light curve, but you wouldn't get this clean, repeating 16.16-hour period. It's too regular, too precise. You need something triggering these pulses in a coordinated rhythmic way. And that brings us back to Loeb's breathing coma hypothesis. If the nucleus has some mechanism, natural or otherwise, that causes it to vent gas in periodic bursts, then each burst inflates the coma, increasing its scattering cross-section and making the whole object brighter. As the material disperses and spreads out, the density drops, scattering efficiency falls, and the object dims. Rinse and repeat every 16.16 hours. This isn't just speculation, it's the only model that fits the constraints. Rotation fails mathematically. Continuous outgassing fails to explain the periodicity. The only option left on the table is pulsed ejection, a breathing coma. And if that's what's happening, then 3I ATLAS is behaving in a way no comet in our catalogue does. Which raises the next question: how big are these pulses, and what kind of physical process could drive them? That's where the numbers get truly staggering. Part 3. The breathing coma, the 25 to the 600 km expansion wave. Per pulse. Imagine standing in front of a giant invisible engine. Every 16.16 hours it fires. Not a steady hum, but a discrete burst. Gas and dust erupt outward, racing into space at hundreds of meters per second, forming a shell that expands like a slow-motion explosion. Then it fades. Then, 16 hours later, it happens again. That's the breathing coma model, and thanks to some careful observations we can actually estimate the scale of each breath. Data from the James Webb Space Telescope, our most powerful infrared eye in the sky, has given us velocity measurements for the outflowing gas and dust from 3I ATLAS. The material is moving at roughly 440 meters per second. That's fast. Not relativistic, not even close to escape velocity for the solar system, but fast enough to carry material far from the nucleus in a short time. Now, let's do the math. If gas and dust are ejected at 440 meters per second, how far do they travel in one 16.16-hour cycle? You multiply velocity by time. 440 meters per second times 16.16 hours. Convert hours to seconds, that's 58,176 seconds, and multiply. You get about 25,600 kilometers. 25,600 kilometers. That's the radius of the expanding shell created by a single pulse. That's roughly twice the diameter of Earth. Every single pulse inflates the coma by a bubble the size of 2 Earths stacked side by side. Think about the visual. Picture the nucleus, tiny, maybe 5 kilometers across, sitting at the center. Every 16 hours it vents a cloud of gas and dust that races outward at nearly half a kilometer per second. The cloud expands into a glowing shell, scattering sunlight, making the whole system bright. Over the next several hours that shell disperses, thins out, becomes transparent. The brightness drops, then the cycle repeats. It's rhythmic, it's powerful, it's completely unlike the steady, passive coma of a normal comet. This model naturally explains the large amplitude brightness swings. When the shell is dense and compact, lots of particles scattering sunlight in a small volume, you get peak brightness. As the shell expands and the particles spread out, the scattering efficiency drops. Fewer particles per unit volume means less light scattered back toward us. The object dims. This mechanism doesn't rely on the orientation of the nucleus. It doesn't matter if we're seeing it broadside or edge-on. What matters is the density and distribution of material in the coma, and that changes every 16 hours like clockwork. Contrast this with continuous outgassing, the standard comet model. In that scenario, the nucleus steadily leaks gas and dust as solar heating drives sublimation. The coma is more or less stable, a constant haze around the nucleus. Sure, there might be some variation as different patches of ice face the sun, but it's gradual, not abrupt. You don't get clean periodicity, you don't get discrete pulses. Continuous outgassing is like a leaky garden hose steady drip, no rhythm. What we're seeing with 3I ATLAS is more like a geyser. It erupts, it stops, it waits, then it erupts again. And this model ties together some other weird observations. Imaging of 3I ATLAS, especially post-perihelion, after its closest approach to the Sun, has shown complex structure in the coma. Expanding halos, jet features, what looks like an anti-tail pointing toward the Sun rather than away from it. These features are hard to explain with passive steady outgassing. But if the object is pulsing, if it's ejecting discrete packets of material at regular intervals, then you'd expect to see layered structure. You'd expect to see multiple expanding shells at different stages of dispersal. You'd expect jets aligned with the ejection events. The breathing coma model predicts exactly this kind of morphology. Of course, there's a caveat. We don't yet have publicly released, calibrated, time-resolved imaging that shows the full expansion and contraction cycle over a complete 16.16-hour period. No one's published a time-lapse video where you can watch the coma inflate, peak in brightness, then fade, then repeat. That data might exist, it might be sitting in some observatory's hard drives, being analysed, calibrated, prepared for publication, or maybe it hasn't been captured yet. Either way, we're working with indirect evidence, velocity measurements, brightness curves, snapshots at different phases. The physics fits, the model works, but the smoking gun visual proof, that's still missing, and we'll come back to why that's such a critical gap. For now, the takeaway is this. If 3I ATLAS is breathing, if it's pulsing out 25,000 kilometre shells of gas and dust every 16 hours, then it's not behaving like any comet we've catalogued. It's dynamic, it's active, it's doing something, and that raises the most important question of all: what's triggering these pulses? What kind of mechanism, natural or otherwise, could produce such a regular, powerful cycle? Part 4. The sunward jet constraint. Why natural models must obey a simple geometry. If we're going to explain these pulses naturally, without invoking anything exotic or artificial, we need a mechanism. The most obvious candidate is thermal. Solar heating drives sublimation of volatile ices on the nucleus. As the nucleus rotates, a patch of ice rotates into sunlight, heats up, and vents gas and dust. When that patch rotates out of sunlight, sublimation stops. The pulse ends. 16.16 hours later, the same patch rotates back into the Sun, and the cycle repeats. This is the sunward jet hypothesis, and it's the natural model that Avi Loeb and others have proposed as the most plausible explanation. It's elegant, it's simple, and it makes a very specific, testable prediction. If pulses are triggered by a sunward-facing ice patch, then the jets, the actual streams of gas and dust being ejected, must point in the direction of the Sun at the moment of peak brightness, or close to it. Because thermal sublimation is driven by solar radiation, the gas and dust will be vented outward from the heated surface, which is the surface facing the Sun. That means the jet direction should correlate with the Sun object geometry. This is what I'll call the Loeb test. It's a geometric constraint. If you observe 3I ATLAS during a brightness peak, and you see jets firing, those jets should be aligned with the Sun object line. If they are, great, natural thermal model holds up. If they're not, if the jets are firing sideways, or even anti-sunward, in directions that don't match solar heating, then you've got a problem. A big problem. Because non-solar aligned jets suggest a mechanism that doesn't depend on where the Sun is, and that opens the door to something much stranger. Why does this matter so much? Because it's a yes or no test. There's no wiggle room. Either the jets point toward the Sun during peak activity, or they don't. Either the timing matches or it doesn't. You can't fudge geometry. You can't hand-wave away the Sun's position. It's one of the clearest discriminators we have between a natural thermal process and something else. Now, let's look at what we've actually observed. Recent imaging from November 2025, stacked exposures from ground-based observatories on November 8th, revealed a complex jet structure around 3I ATLAS. Not one jet, 7 distinct jets. At least 7. Some appear to point roughly sunward, forming what looks like an anti-tail. Others radiate in different directions. The whole thing looks less like a simple geyser, and more like a sprinkler system with multiple nozzles firing in different orientations. This complexity is both fascinating and troubling for the simple sunward jet model. If you've got one volatile patch rotating into sunlight once per rotation, you'd expect one dominant jet. Maybe some secondary features from minor active areas, but the dominant signals should be aligned with the Sun. Instead, we're seeing a whole bouquet of jets, multiple directions, asymmetric structure. It doesn't immediately scream single rotating ice patch heated by the sun. Of course, there are ways to complicate the model. Maybe there are multiple active patches on the nucleus, each with its own rotation phase, each contributing to the total outgassing. Maybe the nucleus is tumbling, not just spinning, which could create more complex jet patterns. Maybe the coma itself is optically thick enough that some jets get obscured or scattered, making the apparent directions misleading. These are all valid caveats. The real world is messy. Comets don't read textbooks, but the lobe test still stands. When 3i ATLAS reaches peak brightness, where are the jets pointing? Do they align with the sun? If imaging shows jets firing during the peak phase, and they're not sunward aligned, then the thermal model is in serious trouble, because solar heating is directional. It doesn't heat the backside of the nucleus. It doesn't heat patches and shadow. If jets fire from the dark side, or perpendicular to the sun, you need a different energy source. Internal heat, radioactive decay, something else entirely. And here's the frustrating part. We don't yet have that definitive time-stamped calibrated observation. We have snapshots. We have images showing jets. We have brightness curves showing the 16.16 hour period. But we don't have a synchronized time-lapse that shows unambiguously, here is the moment of peak brightness. Here is the sun's direction. Here are the jets. They align, or they don't. That observation exists in principle. Someone, somewhere, with access to a major telescope and precise timing could capture it. Maybe they already have, and the data is embargoed. Maybe it's being analysed right now. Or maybe no one's tried yet because getting that kind of coordinated, continuous coverage is hard. Telescopes are oversubscribed. Time is expensive. And the object is faint, requiring long exposures and careful calibration. But until that data comes out, the mystery remains wide open. The natural model is plausible, the geometry test is clear, and if the jets don't pass the test, if they fail the lobe test, then we're looking at something that doesn't fit any comet in our catalogue. And that brings us to the next question. Why hasn't that smoking gun observation been released? What's the hold-up? Part 5. The missing time lapse. Why we don't have the 6 images that would solve everything. Here's the setup. You have an object pulsing every 16.16 hours with a precise, repeating brightness cycle. You have a clear geometric test. Do the jets align with the sun during peak brightness? That could settle whether this is natural or something stranger. And you have some of the most powerful telescopes in human history, including Hubble and James Webb, both capable of high-resolution imaging with precise timing. So why don't we have a publicly released time-lapse that covers a full cycle? Why haven't we seen 6 or 8 images, spaced evenly across 16 hours, showing the coma expand, brighten, pulse and fade, with overlays marking the sun's direction and the jet orientations? Think about what such a time-lapse would show. You'd have the object at hour 0, baseline brightness, coma relatively calm. Hour 3, brightness climbing, jets becoming visible, coma starting to inflate. Hour 8, peak brightness, maximum jet activity, coma at full extension. Hour 12, fading, jets dimming, coma dispersing. Hour 16, back to baseline, and repeat, with timestamps, with solar geometry overlaid, with background stars for calibration. It would be the smoking gun. It would settle the debate. Either the jets fire sunward during the peak, natural model wins, or they don't, and we've got a genuine mystery. So where is it? Let's walk through the possible reasons for the gap, because this isn't trivial. First, scheduling and resource constraints. Getting continuous coverage of an object over 16 plus hours is hard. Most major telescopes don't observe the same target continuously for that long. They're oversubscribed. Astronomers compete for time. Observations are scheduled in blocks, often separated by hours or days. To get a true time-lapse, you'd need either one telescope dedicating more than half a day to this one object, or a coordinated campaign with multiple telescopes handing off as the Earth rotates. Both are doable, but both require significant investment of resources and coordination. Second, proprietary data and embargoes. When a major observatory allocates time to a research team, the resulting data typically isn't released immediately. The team gets exclusive access for a period, often months, to analyse, calibrate and publish their findings. They've invested the effort to propose the observation, justify the science case, and process the data. They deserve first crack at interpreting it. But that means the rest of us wait. If someone captured a full 16-hour time-lapse in August or September 2025, we might not see it publicly until early 2026 or later, after peer review and publication. Third, analysis time. Raw telescope data is not ready for YouTube. It's full of noise, cosmic rays, detector artifacts, atmospheric distortion if it's ground-based. It needs dark frame subtraction, flat fielding, stacking, alignment, photometric calibration. If you're dealing with a faint object like 3i ATLAS, you might need to stack dozens of exposures per time point to build up enough signal. That takes time, weeks easily, maybe months if you're being thorough. Fourth, institutional caution. The claims around 3i ATLAS are bold: heartbeat pulses, possible non-natural activity, potential techno-signature. These are career-defining or career-ending claims depending on how they're received. If you're the team sitting on the definitive data, you're going to be very, very careful. You're going to double-check everything. You're going to run every control you can think of. You're going to consult colleagues, maybe run simulations, maybe wait for additional observations to confirm. Because if you release data suggesting this thing is artificial, or even just deeply anomalous, and you're wrong, you're never living it down. Science is conservative, especially with extraordinary claims, and that conservatism can create delays. Fifth, complexity of the jet structure itself. We've already seen that 3i ATLAS has at least 7 jets, not one, multiple orientations, time-variable morphology. Stacking images over long exposures might blur that detail. You'd need high cadence, short exposures, which means fainter signal per frame, which means more noise, which means more calibration headaches. Capturing the jets in crisp, unambiguous detail across a full cycle is technically challenging. Finally, maybe no one's tried yet. Maybe the community is still catching up. Maybe the brightness periodicity only became clear in the last few months, and coordinated campaigns are being planned but haven't executed yet. Maybe the observation will happen in January 2026 or March, and we're simply ahead of the curve. Here's the implication. Until that time-lapse becomes public, until we have synchronized, calibrated imaging across a full cycle with geometry overlays, we can't definitively settle the natural versus artificial question. We have strong hints. We have models that fit some of the data, but we don't have proof. The test exists, the capability exists, the data might exist, but we, the public, the broader scientific community, don't have access to it yet. And that's the cliffhanger. Someone, somewhere, might be sitting on the frames that could change everything, or those frames are about to be captured. Either way, we're in a holding pattern, waiting for the evidence that will either confirm 3i ATLAS as a weird but natural comet, or push it into entirely new territory. And while we wait, let's explore what that new territory might look like, because the anomalies don't stop with the pulse. Part 6. The anti-tail reconsidered. Dust artifact or sunward thruster plume. Comets have tails. Everyone knows this. A long glowing streamer of gas and dust pointing away from the sun, blown back by solar wind and radiation pressure. It's iconic. It's predictable. Except 3i ATLAS has something else. An anti-tail, a feature that appears to point toward the sun, not away from it. And that's weird. Let's define terms quickly. A normal tail forms because solar radiation and solar wind push lightweight particles, gas molecules, tiny dust grains, away from the sun. The comet's motion through space combined with this push creates a tail that streams behind the comet, always pointing roughly away from the sun. That's the standard setup. An anti-tail, on the other hand, looks like it's pointing sunward. It seems to defy the physics, and astronomers have seen anti-tails before, so they have explanations. Usually it's an optical illusion, a projection effect. If a comet sheds a flat sheet of dust in its orbital plane, and Earth happens to view that plane edge on, the sheet can look like a spike pointing toward the sun. It's not actually sunward moving material, it's geometry playing tricks on your eyes. So the first instinct when you see an anti-tail on 3i ATLAS is to say, okay, projection effect. Dust sheet. Nothing unusual, except the anti-tail on 3i ATLAS appears structured, stable, and it seems to correlate with the pulsation period. It's not just a random dust artifact visible at one moment and gone the next. It's persistent. It shows up in multiple images, and it overlaps with the timing of the brightness pulses. That's harder to explain away as pure geometry. Imaging from November 8, 2025 showed at least 7 distinct jets, some of which appeared to form a sunward-pointing feature, an anti-tail embedded in the broader jet structure. If this is real sunward ejection, material actually being thrown toward the sun, it breaks the normal comet physics. Because you need a force to push material sunward, against radiation pressure, against the solar wind. Gravity alone won't do it. The nucleus is tiny, its gravity negligible. So what's pushing? One possibility, still natural, is that this is heavy dust. Radiation pressure is weak on large particles. If the anti-tail is made of millimetre-sized or larger grains, they might not get blown back as easily. They could follow ballistic trajectories that, depending on ejection velocity and direction, might appear to point sunward from certain viewing angles. This is a stretch, but it's plausible. Complex dust dynamics can sometimes create surprising visual effects. But here's where we enter speculative territory. What if the anti-tail isn't dust dynamics at all? What if it's a plume? Specifically, what if it's a thruster plume, a directed jet of gas and dust being expelled sunward as part of a propulsion system? If 3i ATLAS were an artificial probe, and it needed to adjust its trajectory, one way to do that would be to fire a thruster. If the thruster fires sunward, it produces a reactive force that slows the object down, a braking burn. And the exhaust from that thruster would create a glowing plume pointing toward the sun. This is obviously speculative. We have zero direct evidence of machinery, engines, or artificial control. But as a hypothesis, it ties together three anomalies in one framework. First, the periodic brightness pulses could be the engine firing on a cycle. Second, the structured jets could be multiple thrusters or vents, oriented in different directions for attitude control. Third, the sunward anti-tail could be the exhaust plume from a primary thruster executing a braking maneuver. If you were designing an interstellar probe approaching a solar system, you might want to slow down. Interstellar speeds are high, 3i ATLAS is moving at tens of kilometers per second. If you want to linger, to study the system, to adjust your trajectory for a flyby of a planet or moon, you need to decelerate. A sunward thrust is a natural way to do that. It opposes your motion, slows you down, and if that thrust is pulsed, maybe for thermal reasons, maybe to manage propellant, maybe as part of a duty cycle, you'd see periodic bursts, a heartbeat. Now, before we get carried away, let's acknowledge the natural pitfalls. Dust and gas dynamics around comets are fiendishly complex. Projection effects can fool experienced observers. Jets can point in unexpected directions due to topography, rotation, or subsurface venting. The anti-tail could be perfectly natural, a combination of heavy dust, viewing geometry, and timing coincidence. We've seen weird comet features before that turned out to have mundane explanations. But the convergence is suggestive. Periodic pulses, multi-directional jets, sunward feature, all happening on a 16.16-hour cycle, all defying simple natural models. The thruster hypothesis is wild, yes, but it's not nonsensical. It fits the data as well as, or better than, some of the natural contortions we'd need to explain everything. And this is why the geometric test, the lobe test, is so critical. If the jets fire sunward during peak brightness, and the timing matches solar heating, we can breathe easier. Natural model survives. But if the jets fire at odd angles, or during times when solar heating doesn't make sense, or if the anti-tail shows up when it shouldn't, then we have to seriously consider that we're looking at something operating on a different principle. Not solar-driven sublimation. An operational cycle. Which brings us to the next idea. What if 16.16 hours isn't a rotation period at all? Part 7. The operational frequency. Hypothesis. 16.16 hours as a duty cycle, not a day. Stop thinking about 16.16 hours as a rotation period. Start thinking about it as a duty cycle, an operational frequency, a programmed interval. Because if 3i ATLAS is artificial, if it's a probe, a device, a relic of some long-vanished technology, then that precise, repeating rhythm starts to look less like physics and more like engineering. Think about how machines work. Spacecraft have cycles. Satellites perform station-keeping burns at regular intervals. Probes execute time sequences, data collection, transmission, instrument calibration, thermal regulation. Even simple devices have duty cycles. Your refrigerator compressor doesn't run continuously. It cycles on and off to maintain temperature. Your computer's cooling fan ramps up and down based on load. Periodicity is a hallmark of designed systems, not just natural ones. What if 3i ATLAS is doing something similar? What if every 16.16 hours it executes a sequence? Maybe it vents waste heat. Maybe it adjusts its spin or orientation. Maybe it purges gas or dust built up from interstellar medium impacts. Maybe it fires thrusters for minor trajectory corrections. Maybe it recalibrates sensors. We have no way to know the specific function, but the principle is the same: a machine performing scheduled maintenance or operations on a timer. This idea shifts the entire interpretive framework. Instead of asking, why does this comet rotate every 16 hours? You ask, what operation is this probe running every 16 hours? And suddenly, the anomalies start making more sense. The brightness pulses, venting operations, waste heat dumps or thruster firings that temporarily inflate a plume or coma-like cloud around the probe, the multi-directional jets, multiple thrusters or vents oriented for different purposes, attitude control, stabilization, course corrections, the anti-tail, primary thruster firing sunward for deceleration. Real-world analogues exist, even in our primitive spaceflight. Consider the International Space Station. It performs periodic boost burns to maintain altitude, counteracting atmospheric drag. Those burns happen on a schedule, sometimes weeks apart, sometimes more frequently. If you were observing the ISS from a distance and couldn't resolve its structure, you might see periodic brightness changes as the thrusters fire and create exhaust plumes that reflect sunlight. You might see jets. You might wonder what natural process could explain it, when the answer is simply, it's a machine doing machine things. Or consider thermal management. Spacecraft generate heat from electronics, power systems, even from sunlight absorption. That heat has to go somewhere. Some spacecraft use radiators, some vent, coolant. Some perform periodic rotations, barbecue rolls to distribute heat evenly. If 3i ATLAS has any kind of internal power source, maybe a radioisotope thermoelectric generator, maybe something more exotic, it would need to dump waste heat. Venting gas periodically could serve that function. Heat gas with waste thermal energy, vent it, repeat. 16.16 hours per cycle. Now, the obvious objection. We have no direct evidence of engineering materials, no metals, no electronics, no structures. The spectral data we have so far is limited, and we'll get to some intriguing hints in a moment, but nothing screams spacecraft. So how do we reconcile the operational frequency hypothesis with the lack of obvious technosignatures? One answer: stealth isn't the goal, but durability is. If you're building a probe to survive interstellar space for thousands or millions of years, you're going to encase it in something protective. Ice is actually a decent shielding material. It blocks radiation, it's easy to acquire in the outer reaches of a solar system, and it sublimates away as you approach a star, potentially revealing the core structure only near perihelion. So maybe 3i ATLAS is a probe encased in ice. The ice provides the coma, the jets, the comet-like appearance, but underneath, there's something else. Another answer, maybe the operational cycle is biological or quasi-biological, not a machine in the sense of gears and circuits, but something organic, something we wouldn't recognize as technology, because it doesn't look like our technology. Speculative? Absolutely. But if we're entertaining the artificial hypothesis at all, we have to let go of anthropocentric assumptions about what artificial means. The multidirectional jets support the operational frequency idea. If this were a simple rotating nucleus with one active patch, you'd expect one dominant jet aligned with the sun. Instead, we see at least 7 jets in different directions. That's easier to explain if you have multiple vents or thrusters, each serving a specific function. Attitude control requires thrust in multiple directions. You need pitch, yaw, roll authority. One thruster won't cut it. You need a cluster, and the periodicity is so precise. 16.16 hours, not 15, not 17, not a range of 14 to 18 depending on conditions. 16.16, repeating like a metronome. Natural rotation can be that regular, sure, asteroids spin with consistent periods, but natural outgassing driven by solar heating and surface irregularities tends to be messier, variable, noisy. The cleanliness of the period hints at something locked in, something programmed. Of course, this remains speculative. We don't have the evidence yet to declare 3i ATLAS artificial, but the operational frequency hypothesis is on the table, and it's not crazy. It fits the data, it unifies the anomalies, and it makes testable predictions. If it's a duty, cycle, we should see consistency across multiple cycles. minimal drift, and possibly correlation with other periodic signals like radio emissions or infrared pulses if anyone's looking. Which brings us to a potential clue that might tip the scales, the nickel anomaly. Part 8. The nickel anomaly, heavy element abundance and its implications. Comets are supposed to be dirty snowballs. Ice, rock, organic compounds, maybe some silicates and carbon-bearing molecules. What they're not supposed to have is heavy metals, certainly not in unusual abundances, so when preliminary reports started circulating about spectral signatures from 3I ATLAS, showing elevated nickel or nickel-bearing compounds, it raised eyebrows. Because nickel doesn't belong in a comet's coma, not in significant amounts. Let me caveat this right now. The heavy element data is not fully confirmed or peer-reviewed as of the latest public information. Some reports are anecdotal. Some come from early spectroscopic passes that might have calibration issues. We don't have a definitive published spectral analysis declaring 3I ATLAS is rich in nickel. But the whispers are there, and they're worth exploring because of what they'd mean if true. Typical comets, when analysed spectroscopically, show emission lines from molecules like water, carbon monoxide, carbon dioxide, cyanide, hydroxyl radicals, stuff you'd expect from sublimating ices and organic-rich dust. Metals, if present at all, show up as trace contaminants, sodium, iron maybe, in tiny amounts. Nickel is a heavy element. It doesn't sublimate at the temperatures comets experience. It's not part of the volatile ice budget. For nickel to appear in the coma, you'd need to liberate nickel-bearing dust particles and get them into the gas flow. That's unusual. Why does nickel matter? Because it's an engineering material. Humans use nickel in alloys, stainless steel, superalloys for high-temperature applications, structural components in aerospace. Nickel is strong, corrosion-resistant, heat-tolerant. If you were building a spacecraft to last for interstellar durations, nickel alloys would be on your materials list. So if 3I ATLAS is showing nickel, it's at least consistent with the artificial hypothesis, even if it doesn't prove it. Natural explanations do exist. Maybe 3I ATLAS comes from a star system with a different primordial composition, richer in heavy elements due to prior supernovae enriching the local interstellar medium. Maybe it's a fragment of a differentiated body, something that once had a molten core where heavy metals sank and concentrated, and 3I ATLAS is a chunk blasted off that core. In our solar system, metallic asteroids exist, remnants of shattered protoplanets. An interstellar version isn't impossible, but here's the challenge. Metals don't sublimate. They don't turn into gas at the low temperatures and pressures in the outer solar system. To get nickel-bearing particles into the coma, you need a mechanism to physically eject them. Maybe micrometeorite impacts blast dust off the surface. Maybe deep internal heating, radioactive decay, tidal stressing, melts or vaporizes subsurface material, which then erupts. But both scenarios are stretching. Cometary nuclei aren't known for smelting operations. Alternatively, if 3I ATLAS is artificial, the nickel could be debris, where particles from moving parts, oxidation products from metal surfaces exposed to the interstellar medium, exhaust contaminants from propulsion systems. If the jets we're seeing are vents or thrusters, and those systems involve metal components, trace amounts of metal could be entrained in the outflow, not because the probe is made of nickel, but because nickel is a byproduct of operation. Think about rocket exhaust. Even chemical rockets produce trace metal emissions, combustion chamber erosion, nozzle ablation. If 3I ATLAS uses some kind of thermal or ion propulsion, metallic contaminants in the exhaust plume are plausible. Not dominant, not the bulk of the outflow, but detectable if you're looking with sensitive spectroscopy. The other intriguing aspect is energy budget. Sublimating ice requires solar energy or internal heat, but it's a well-understood process. Venting metal particles requires either mechanical ejection, like a dust gun, or temperatures high enough to vaporize refractory materials. Both suggest energy sources beyond passive solar heating. Radioisotope decay could do it. A small internal reactor could do it. Even stored chemical energy, if the object has reserves. But these are all more exotic than sun heats ice sublimates. So what would confirming heavy metal content mean? It would radically shift the conversation. A comet with elevated nickel is weird. A comet with elevated nickel that also pulses every 16 hours with multi-directional jets and a sunward anti-tail. That's not weird. That's suspicious. It doesn't prove artificiality, but it stacks the deck. It adds another anomaly to a growing pile. And here's the thing. If the nickel signature is real, it should be verifiable. Spectroscopy is mature technology. Multiple observatories can target 3I ATLAS, take high-resolution spectra, cross-check results. If nickel is there, confirmation will come. If it's not, if the early reports were artifacts or misidentifications, that will come out too. Science is self-correcting. But we're in the waiting phase where rumours and preliminary data circulate faster than peer review. What's clear is that 3I ATLAS doesn't fit neatly into any existing category. Not a normal comet, not a typical asteroid, not like Oumuamua, which was small and dark and weird in different ways. 3I ATLAS is in a class of its own, possibly a class of one. And that brings up a crucial question. Has anything like this ever been seen before? Part 9. Hidden Context. Historical pulse phenomena in comets and why 3 ATLAS doesn't fit any catalogue. Comets misbehave. They fragment. They flare. They produce jets that fire at odd angles. They spin. They tumble. They disintegrate. Cometary science is full of surprises. So when 3I ATLAS showed up pulsing like a heartbeat, the first thing astronomers did was check the archives. Has any other comet done this? Has anything in the historical record shown stable, hour scale, high amplitude periodic brightness variations like we're seeing now? The answer, as far as we can tell, is no. Nothing matches. Let's walk through what we do see in comets. Rotation-driven light curves are common. An irregularly shaped nucleus spins, and as its cross-section changes, brightness varies. But those variations are typically small, a few %, and the periods are usually hours to days. We've measured rotation periods for hundreds of comets and asteroids. Some are fast spinners, hours, some are slow, days. But the amplitude is modest because the nucleus itself contributes little to the total light once a coma forms. Outbursts are another known phenomenon. Comets sometimes brighten suddenly by factors of 2, 5, even 10, over the course of hours or days. These outbursts are thought to be triggered by sudden exposure of fresh ice. Maybe a cliff collapses, maybe a subsurface pocket of volatile ice breaks through to the surface and explosively sublimates. But outbursts are sporadic, unpredictable. They don't repeat on a clock every 16 hours. Some comets show quasi-periodic activity tied to solar distance. As they approach the Sun, activity ramps up. As they recede, it drops. This creates a brightness curve that peaks near perihelion and fades afterward. But that's a slow, seasonal variation over weeks and months, not an hour-scale pulse. Jet activity can be episodic. Some comets have jets that turn on and off as active regions rotate into and out of sunlight. Those jets can create periodic brightness variations if the jet is bright enough and the viewing geometry is favourable. But again, the amplitude is usually small, and the jets tend to be solar aligned, firing when the active patch faces the Sun. 3I ATLAS has jets that don't all align that way. Fragmentation events can produce sudden brightness changes. If a comet splits into pieces, each piece can develop its own coma, and the total brightness can spike. But fragmentation is a one-time event, or at most a series of discrete events separated by long intervals. It doesn't produce a regular 16-hour cycle. So where does that leave us? We have a catalogue of cometary behaviours, rotation, outbursts, jets, fragmentation, seasonal variation, and none of them quite fit what 3I ATLAS is doing. The periodicity is too regular, the amplitude is too large, the jet structure is too complex. It's a combination of features that doesn't match anything in the historical record. Part of the problem is observational. Until very recently, we didn't have the capability to monitor faint comets continuously over long timescales with high photometric precision. Most cometary observations were snapshots, images taken at intervals of days or weeks, not hours. If a comet pulsed every 16 hours, we might miss it entirely, or see only scattered data points that didn't reveal the underlying pattern. The technology to detect this kind of behaviour, sensitive cameras, automated sky surveys, machine learning pipelines that flag periodic signals, is new. Very new. Last decade new. So it's possible that objects like 3I ATLAS have passed through our solar system before, and we simply didn't notice. We didn't have the tools, or we had the data but didn't analyse it carefully enough. That's a humbling thought. How many weird objects have we missed because we weren't looking for weirdness? But it's also possible that 3I ATLAS is genuinely unique. Interstellar objects are rare. We've only confirmed a handful: Oumuamua, Borisov, and now 3I ATLAS. Each one has been different. Oumuamua was small, elongated, maybe tumbling, with a non-gravitational acceleration we still don't fully understand. Borisov looked like a normal comet. Big coma, normal composition, ordinary behaviour. 3I Atlas is somewhere in between, comet-like in appearance, but with behaviour that defies the comet playbook. This raises a taxonomic challenge. How do we classify 3I Atlas? Is it a comet? An interstellar asteroid with volatile ice? A new category? Pulsing interstellar visitor? The standard classifications, comet, asteroid, dwarf planet, are solar system centric. They were developed based on objects that formed in our solar system, orbit our sun, follow our rules. Interstellar objects don't have to play by those rules. They come from different stellar environments, different formation histories, different evolutionary pathways. Maybe we need new categories. Maybe 3I Atlas is the first example of a class we haven't named yet. Dynamic coma objects, pulsing visitors, active interstellar travellers. Or maybe it's a one-off, a freak, an outlier so strange that it defies classification entirely. The skeptics will say, and they're right to be cautious, that you can't define a new class based on one object. You need multiple examples. You need statistics. You need to show that the features are reproducible, not just noise or measurement error. Fair enough, but every new class starts with one. The first pulsar was a glitch in the data until more were found. The first exoplanet was controversial until the second and third were confirmed. 3I Atlas might be that first example, or it might remain alone. Either way, it's pushing the boundaries, and if we're willing to entertain even briefly that 3I Atlas might be artificial, that it might be a probe, a relic, something built rather than accreted, then the question shifts from what is it to what is it doing? What's the mission? What's the purpose? Part 10. The big scope speculation. If it is artificial, what is it doing? Let's play the game. Let's assume for the next 1,000 words that 3I Atlas is artificial, not a comet, not a natural object, a probe, a device, a relic of technology from some civilization that existed long enough ago or far enough away that we'll never meet them. What could it be doing? What would explain the behaviour we're seeing? The 16-hour pulse, the jets, the anti-tail, the possible nickel signature? The first and most obvious possibility is reconnaissance. Interstellar probes sent out to explore other solar systems, gather data, and either report back or store information for later retrieval. Think of the Voyager probes, but scaled up. Voyagers are leaving our solar system now, carrying data about Earth, our civilization, our science. They're moving slowly by interstellar standards, but they're moving. In 100,000 years, they'll pass near other stars. If another civilization did the same thing, and their probe happened to pass through our solar system, we'd see something like 3I Atlas. Small, fast, possibly equipped with instruments to measure stellar radiation, magnetic fields, particle densities, planetary positions. Why the pulses? Maybe the probe performs periodic scans or data dumps. Every 16 hours it activates sensors, collects a batch of measurements, then powers down to conserve energy. The pulse could be a waste heat vent, sensors generate heat, instruments need cooling, venting gas is a simple way to radiate excess thermal energy. The jets could be attitude control, small thrusters adjusting the probe's orientation to keep antennas or instruments pointed in the right direction. The sunward anti-tail fits this too. If the probe is slowing down, performing a braking burn to linger in the inner solar system longer, or to adjust its trajectory for a closer look at something interesting, it would fire thrusters sunward. That generates a reactive force opposite to its velocity, decelerating the probe. The exhaust plume creates the anti-tail. Simple orbital mechanics. Another possibility is station keeping. Maybe 3I Atlas isn't just passing through. Maybe it's been here before. Maybe it's on a long elliptical orbit that brings it back to our solar system every few thousand or million years. Each visit it performs maintenance, checks systems, recalibrates instruments, adjusts its orbit slightly to account for perturbations. The 16-hour cycle could be a maintenance routine. Power up, run diagnostics, vent accumulated gas or dust, power down, repeat. Or maybe it's a sampler. As it moves through the solar system, it's collecting particles, solar wind, dust, maybe even atmospheric molecules if it passed through the upper atmosphere of a planet. The jets we see could be periodic purges, venting sample chambers, clearing, filters, dumping contaminated material to make room for new samples. This would explain multi-directional jets. different vents for different sampling systems, each oriented to avoid cross-contamination. More speculatively, it could be a beacon, a communication device. The 16-hour pulse could be a timing signal, a way to announce I am here to anyone watching. The brightness variations, the jets, even the anti-tail, these could all be deliberate signals, encoded information in the timing and structure of the emissions. We're not detecting radio signals, but that doesn't mean there isn't a message. Light itself can carry information. Pulses, pauses, patterns, these could encode data in a language we don't recognise yet. Then there's thermal regulation. If 3i ATLAS has an internal power source, a radioisotope thermoelectric generator, a small reactor, something exotic, it needs to dump heat. In space, the only way to shed heat is radiation. But if you're small, and your surface area is limited, passive radiation might not be enough. Venting hot gas is an active cooling mechanism. Heat the gas with waste thermal energy, eject it, repeat. The periodicity could reflect the thermal cycle. Heat builds up, triggers a vent, system cools, heat builds again. Now, the big question, if it's a probe, where's it from, and how old is it? Interstellar distances are vast. Even at 3i ATLAS's speed, tens of kilometres per second, it would take tens of thousands of years to cross from the nearest star. If it originated from a civilization around a nearby star, and that civilization is still around, why haven't they contacted us? Maybe they have, and we didn't notice. Maybe 3i ATLAS is the contact, a slow, passive messenger we're only now starting to recognise. Or maybe the civilization is gone. Maybe 3i ATLAS is a relic, a ghost ship from a long-dead culture. It launched millions of years ago when its creators were thriving, exploring, expanding. Then something happened. War, collapse, natural disaster, extinction. The probe kept going, oblivious, executing its programming long after anyone cared. Now it drifts between stars, a fossil of technology, still functional but purposeless. That's a haunting thought. A lonely probe, wandering the galaxy, performing its routine every 16 hours because that's what it was built to do. No one listens. No one's waiting for the data. It just goes forever, until some component fails and it dies in silence. Or maybe it's part of a swarm. Maybe its creators sent out thousands, millions of probes, scattering them across the galaxy like seeds. Most fail. Most drift into stars or get destroyed by impacts. But some survive. Some make it to other systems. 3i ATLAS could be one of many. We just haven't detected the others yet because they're dark, dormant, or passing too far from the sun to activate. Energy requirements are a challenge. Keeping a probe operational for thousands or millions of years requires durable power. Radioisotope generators work for decades, maybe centuries if the design is robust. But eons? You'd need something longer lived. Maybe the probe collects energy from cosmic rays. Maybe it has a stored chemical or nuclear fuel reserve. Maybe it harvests hydrogen from the interstellar medium and fuses it. Speculative, but not impossible. Durability is another hurdle. Interstellar space is not empty. There's dust, gas, cosmic rays, radiation. Over long timescales, impacts and erosion would degrade any structure, unless you shield it. Encase it in ice, rock, or a protective shell. Let the outer layers ablate and renew. 3i ATLAS could be a probe cocooned in ice, accreted over millions of years in the interstellar medium. The ice provides protection, and as it approaches a star and warms up, the ice sublimates, revealing the core and creating the comet-like appearance we see. Does any of this prove 3i ATLAS is artificial? No, absolutely not. We have no direct evidence, no radio signals, no obvious structures, no definitive spectral signatures of technology. Everything I've described is speculation, a thought experiment. But it's not baseless speculation. The anomalies are real, the periodicity is real, the jets are real, the anti-tail is real. And none of them fit comfortably into the natural comet model. So the artificial hypothesis stays on the table, not as the leading explanation, but as a possibility that deserves attention. Because if we dismiss it out of hand, and it turns out to be true, we'll have missed one of the most important discoveries in human history. And if it's not true, if 3i ATLAS is just a very weird comet, then figuring out what natural process produces this behaviour will teach us something profound about how comets work, how interstellar objects evolve, and what's possible in the universe. Either way, 3i ATLAS matters, and while we wait for more data, let's zoom out. Because 2025 has been a year of strange signals, unexplained phenomena, and breakthroughs that hint we're on the edge of something bigger. Part 11. December 2025. Breakthrough. The new neutrino burst from the galactic centre. December 2025 brought another anomaly to add to the pile, a burst of high-energy neutrinos from the direction of the galactic centre. Not a steady background trickle, but a discrete spike. Dozens of neutrino events detected over a period of the hours, all pointing back to the same region of sky. The detectors lit up, and the physics community started asking the same question they're asking about 3I ATLAS. What natural process explains this? Neutrinos are ghosts. They're nearly massless particles that barely interact with matter. Trillions of them pass through your body every second, and you never notice because they zip through atoms like they're not even there. Detecting neutrinos requires massive detectors, tanks, of water or ice buried deep underground or under Antarctic ice, because you need enormous volumes to catch even a handful of interactions. When neutrinos do interact, they leave a tiny flash of light, a Cherenkov glow that sensors can pick up. Most neutrinos are background noise. They come from the sun, from cosmic rays hitting the atmosphere, from supernovae in distant galaxies. But a burst, a spike of high-energy neutrinos all coming from the same direction in a short time window, that's unusual. That suggests a specific energetic event. Maybe a black hole flare, matter spiraling into the supermassive black hole at our galaxy's core, heating up and emitting radiation across the spectrum, including neutrinos. Maybe a magnetar glitch, a neutron star's magnetic field rearranging explosively. Maybe something we haven't thought of yet. Here's the connection to 3I ATLAS. Both are periodic or pulsed signals. Both challenge standard models. Both force us to ask whether we're seeing natural astrophysical processes operating in extreme regimes, or whether we're glimpsing something else, something more organised, more structured. Neutrino bursts from the galactic centre could be natural, probably are natural, but if they repeat, if they show periodicity, if they correlate with other signals, radio, optical, gravitational waves, then the picture gets more interesting. Imagine a universe more active than we assume. Not a cold, sparse void punctuated by occasional stellar flares, but a place where energy flows, where structures pulse and breathe, where signals propagate across vast distances. 3I ATLAS pulsing every 16 hours, neutrino bursts from the galactic core, fast radio bursts from distant galaxies, repeating on unpredictable schedules, gamma-ray transients, X-ray flickers. The universe is full of clocks, and we're just starting to hear them tick. This isn't mysticism, it's pattern recognition. When you start finding anomalies in multiple, unrelated contexts, you have to ask whether your models are too narrow. Are we categorizing things as comet, natural emission, background noise? Because those are the boxes we've built, not because those labels accurately describe reality. Maybe the universe has more categories than our taxonomy allows. The neutrino burst, if it becomes a recurring phenomenon, if more detections follow, could hint at periodic activity at the galactic centre. And that would parallel 3I ATLAS, periodic activity in an object we didn't expect to be periodic. Both push us to expand our thinking. Both remind us that the universe is under no obligation to fit our preconceptions. The humility here is crucial. We've only been doing serious neutrino astronomy for a few decades. We've only been detecting interstellar objects for a few years. Our sample sizes are tiny. Our instruments are crude compared to what we'll have in 50 or 100 years. We're cavemen with telescopes glimpsing shadows on the walls of Plato's cave and trying to infer the shapes outside. Most of what we see, we misinterpret. Some of what we see we ignore because it doesn't fit. 3I ATLAS might be the first of many. The neutrino bursts might be the start of a new catalogue. Or both might be flukes, one-offs, noise. We don't know yet. But the fact that both appeared in the same year, both defying easy explanation, suggests we're in an era of discovery, and the tools we're building, AI-driven sky surveys, automated anomaly detection, continuous monitoring, are about to accelerate that discovery. Part 12, the 2025 AI-driven sky survey revolution. 2025 is the year sky surveys went machine mode. Observatories around the world are deploying AI and machine learning to sift through the torrents of data pouring in from automated telescopes. Every night, these instruments capture terabytes of images, stars, galaxies, transients, asteroids, comets. Far too much for humans to analyse manually, so the machines take over, algorithms trained to spot anomalies, detect patterns, flag anything that doesn't fit the baseline. This is how 3i Atlas's pulse was likely discovered, not by a human staring at light curves, but by an automated pipeline that noticed periodic brightness variations and flagged them for follow-up. The algorithm doesn't care what the object is supposed to be, it just looks for deviations from expectation, and when it finds one, it alerts the astronomers, who can then dig deeper. The revolution here is scale and sensitivity. Before AI, detecting subtle periodicities required dedicated observation campaigns. You'd have to deliberately monitor an object for hours or days, collect data, analyse it manually. Now that happens automatically. The AI watches everything all the time. If something pulses, flickers, or changes in an unexpected way, the AI catches it. This means we're going to find more objects like 3i Atlas, not because they're becoming more common, but because we're finally looking properly. Think of it as turning on the lights. For most of astronomical history, we've been observing in snapshots. Take an image, wait. Take another image, compare them, look for changes. But if something changes on an hour scale, and you're only looking once a night or once a week, you miss it. Now, with continuous monitoring and AI analysis, we're watching in real time, or close to it. And the things we're seeing, the fast transients, the microflares, the periodic pulses, these were always there. We just couldn't see them. This has huge implications for interstellar object research. If 3i Atlas is the first pulsing interstellar visitor we've detected, it's probably not the only one. There could be dozens, hundreds, passing through the solar system every year, unnoticed because they're faint or because their behaviour is subtle. With AI surveys, we'll catch them, we'll build a catalogue, and once we have a catalogue, we can start asking statistical questions. How common are pulsing visitors? Are they all from interstellar space? Or do some originate in the Oort cloud? Do they cluster in certain orbits or compositions? Are they natural, or could some be artificial? The same applies to neutrino bursts, fast radio bursts, gamma-ray transients. AI can correlate signals across different wavelengths, different instruments, different timescales. If a neutrino burst coincides with an optical flare and a radio pulse, the AI will catch that. If 3i Atlas's brightness pulses correlate with faint radio emissions or infrared spikes, the AI will flag it. Humans are good at asking questions. Machines are good at finding patterns. Together, we're about to uncover a lot of weird stuff. And here's the hopeful part. In a few years, we might look back at 3i Atlas not as a bizarre one-off, but as the first example of a new class. Maybe by 2030, we'll have detected 50 pulsing interstellar objects. Maybe we'll have a taxonomy, Type A pulsars with 16-hour periods, Type B with 8-hour periods, Type C with irregular bursts. Maybe we'll have ruled out the artificial hypothesis because natural models finally catch up. Or maybe the artificial hypothesis will strengthen because some of these objects show features, repeating signals, trajectory adjustments, spectral anomalies that natural processes can't explain. Either way, the AI revolution is the enabler. It's the tool that lets us see the forest and the trees, the signal and the noise. And as the surveys ramp up, Rubin Observatory coming online, new space telescopes launching, more neutrino detectors activating, we're going to drown in data. The only way to survive that flood is to let the machines help. They don't get tired, they don't get bored, they don't overlook the weird object in the corner of the frame because it doesn't look interesting. They check everything. And in that exhaustive checking, they'll find the anomalies we need to push science forward. 3i Atlas is a preview, a glimpse of what's coming. The universe is full of surprises, and we're finally building the tools to find them. But while we wait for that wave of discovery, we should note that 2025 also delivered a blow to one of physics' biggest hopes. Part 13. This year's dark matter shock. The null results from 3 major experiments. Dark matter is one of the biggest mysteries in physics. We know it exists because we can see its gravitational effects. Galaxies spin too fast. Galaxy clusters hold together too tightly. Light bends around massive objects more than visible matter can explain. Something invisible, something that doesn't emit or absorb light, is pulling on everything. We call it dark matter, and it makes up about 85% of the matter in the universe. But we've never directly detected it. The evidence for dark matter is overwhelming, even if indirect. When astronomers measure the rotation curves of spiral galaxies, how fast stars orbit at different distances from the galactic centre, they find something strange. Stars far from the centre move just as fast as stars closer in. That shouldn't happen. Based on the visible matter, stars, gas, dust, the outer stars should be moving much slower, following the same orbital mechanics that govern planets around the Sun. But they don't. They're moving too fast. Something invisible must be holding them in their orbits, providing extra gravitational pull. That something is dark matter. Galaxy clusters show the same effect, but even more dramatically. These clusters contain hundreds or thousands of galaxies, all bound together by gravity. When you add up all the visible matter in the galaxies, all the stars, all the gas, everything we can see, it's not nearly enough to hold the cluster together. The galaxies are moving too fast, they should be flying apart. Yet the clusters remain stable, which means there must be far more mass present than we can see. Dark matter again. Then there's gravitational lensing. Einstein's general relativity predicts that massive objects bend space-time, and light follows that curvature. When light from a distant galaxy passes near a massive foreground object like a galaxy cluster, it bends, creating distorted or multiple images of the background galaxy. By measuring how much the light bends, you can calculate the mass of the foreground object. And every time astronomers do this, they find the same result. The total mass is much greater than the visible mass. The invisible mass, the dark matter, dominates. So we know it's there. The question is, what is it? For decades, the leading hypothesis has been WIMPs, weakly interacting massive particles. Theoretical particles that interact with normal matter only through gravity and the weak nuclear force. If they exist, they're constantly streaming through us, through Earth, through everything, but so rarely interacting that detecting even one requires enormous detectors and years of patience. Labs around the world have built these detectors, tanks of liquid xenon, germanium crystals, scintillator arrays, deep underground to shield from cosmic rays, waiting for the telltale signal of a WIMP bumping into a nucleus. The theory behind WIMPs is elegant. In the early universe, shortly after the Big Bang, particles were created and annihilated in a hot, dense plasma. As the universe expanded and cooled, some particles survived, the ones we see today, like protons and electrons. WIMPs, if they exist, would have been created in that same early plasma. Their interaction rate with normal matter would be just right so that the number surviving to the present day matches the observed dark matter density. It's a natural prediction of several extensions to the standard model of particle physics, particularly supersymmetry. So the experiments were built, massive detectors, sometimes tons of target material, placed deep underground to filter out cosmic ray noise. The idea is simple. If WIMPs are streaming through Earth constantly, occasionally one will collide with a nucleus in the detector. That collision will cause the nucleus to recoil, depositing a tiny amount of energy that sensitive instruments can detect. It's like trying to catch rain by holding out a bucket, except the rain is invisible and almost never hits anything. 2025 saw 3 major dark matter experiments release their latest results. All 3 reported null detections. No WIMPs, no signals above background noise, years of data collection, exquisite sensitivity, and nothing. Again. The names of these experiments are technical. Lux Zeppelin, Xenon T, Pandax, but the story is the same. Each one represents a decade or more of work by hundreds of scientists. Each one pushes the sensitivity limits further than the generation before. Each one narrows the allowed parameter space for WIMPs, the range of masses and interaction strength that could still be hiding, and each one comes up empty. This is the latest in a long string of null results, stretching back over a decade. Every few years the detectors get more sensitive, the exposure times get longer, and the physicists announce they've ruled out another chunk of parameter space. But they haven't found the particles. Dark matter remains dark. The optimistic interpretation is that we're getting closer. We've ruled out large swaths of parameter space, narrowing the possibilities. WIMPs, if they exist, must have properties that make them even harder to detect than we thought. Lower masses, weaker interactions, something that keeps them just out of reach of current experiments. Build bigger detectors, run longer, and eventually we'll find them. The pessimistic interpretation is that WIMPs don't exist, that the elegant theory, the natural prediction from supersymmetry, is wrong. That dark matter is something else entirely, something we haven't thought of yet, or something that can't be detected with these methods. And if that's true, decades of effort and billions of dollars of investment have been chasing a phantom. Why does this connect to 3I Atlas? Because both expose the limits of our models. Dark matter was supposed to be WIMPs. The standard model of particle physics, extended slightly, predicted them. Experiments were built to find them, and they didn't. So now physicists are scrambling to rethink. Maybe dark matter isn't WIMPs. Maybe it's axions, or sterile neutrinos, or primordial black holes, or something weirder. The models are being revised, expanded, or abandoned. 3I Atlas challenges the standard comet model the same way. Comets are supposed to behave a certain way, rotate, outgas passively, brighten and fade gradually as they approach and recede from the sun. 3I Atlas doesn't do that. It pulses, it jets, it defies the playbook. So we're forced to expand the model, consider new mechanisms, maybe even entertain the possibility that it's not a comet at all. Both cases highlight a broader issue. Science builds models based on the data we have. Those models work well until they don't. When anomalies appear, we have two options: tweak the model to accommodate the anomaly, or admit the model might be wrong and start over. The conservative approach is to tweak, add parameters, introduce new variables, complicate the equations until they fit. But sometimes, the anomaly is telling you something more fundamental. Sometimes, it's saying your framework is broken. The history of physics is full of examples. Newtonian mechanics worked beautifully for centuries, explaining planetary orbits, projectile motion, everything from falling apples to the tides. Then came Mercury's orbit. The planet's perihelion, the point of closest approach to the Sun, precessed slightly faster than Newtonian mechanics predicted. Astronomers tried tweaking the model. Maybe there was another planet closer to the Sun, perturbing Mercury's orbit. They even named it Vulcan. They searched for decades. It didn't exist. The real answer was that Newtonian mechanics was incomplete. Einstein's general relativity, which accounts for the curvature of spacetime near massive objects, predicted Mercury's precession exactly. No new planet needed. The framework itself had to change. Dark matter might be one of those cases. Maybe the problem isn't that we haven't found WIMPs yet. Maybe the problem is that WIMPs don't exist, and dark matter is something completely different, something we haven't even theorized yet. Maybe it's not particles at all. Maybe it's a modification of gravity at large scales. Maybe it's something we can't detect because it doesn't interact with our detectors in any way we've imagined. Modified gravity theories exist. MOND, Modified Newtonian Dynamics, proposes that gravity behaves differently at very low accelerations, the kind experienced by stars in the outer regions of galaxies. With the right modification, you can explain galactic rotation curves without invoking dark matter. But MOND struggles to explain galaxy clusters and gravitational lensing. It's not a complete replacement. Other theories try to modify general relativity itself, introducing new fields or higher dimensional effects. None have gained widespread acceptance yet. Or maybe dark matter is primordial black holes, tiny black holes formed in the early universe, not from stellar collapse but from density fluctuations shortly after the Big Bang. These would be gravitationally bound objects, not particles, and they wouldn't emit light or interact via any force except gravity. They'd be functionally invisible, contributing to the mass budget but undetectable by WIMP experiments. Recent observations have constrained this possibility too, ruling out large ranges of black hole masses, but some windows remain open. And here's a wild thought. What if some fraction of dark matter isn't diffuse particles but objects? Small, dark, dead remnants of ancient civilizations, probes, debris, structures, scattered through the galaxy. Not enough mass to explain all dark matter, but maybe a detectable fraction. If interstellar probes are drifting through space, dark and inactive until they pass close to a star, they'd be invisible most of the time. We'd only detect them when they light up, like 3I Atlas. The rest would contribute to the missing mass, unnoticed. This is wildly speculative, bordering on science fiction, but consider the numbers. The Milky Way galaxy is about 13 billion years old. If intelligent civilizations arise, build technology, and send out probes, how many probes could accumulate over billions of years? If even a tiny fraction of civilizations do this, and if probes survive for millions of years, the galaxy could be saturated with technological debris. Most would be dead, dark, undetectable. A tiny fraction might still be operational, lighting up when they pass near stars. Could this contribute meaningfully to dark matter? Probably not. The mass budget doesn't work. Dark matter is 85% of the total matter. To explain that with probes and debris, you'd need an implausible density, millions of tons of technological artifacts per cubic light-year of galactic volume. Civilizations would have to be extraordinarily common, and their technology-building phase extraordinarily prolific to generate that much mass. But it doesn't have to explain all dark matter to be interesting. If even a small fraction, say 0.1%, of the missing mass is technological artifacts, that's still a staggering amount. And it would mean that the galaxy is full of these objects drifting, waiting to be discovered. 3I Atlas could be one, Oumuamua could be another. The fact that we've detected multiple interstellar visitors in just a few years, after never seeing any before, suggests we're just beginning to sample a population that's been there all along. Speculative? Absolutely. But the point is, the failure to detect dark matter via expected channels should open our minds to more creative hypotheses. We've been looking for particles in underground labs. Maybe we should also be looking at the sky, at the small, fast, dark objects zipping through the solar system. Maybe some of them are the dark matter we've been missing. Not all of it, not most of it, but maybe a detectable, measurable fraction. And if so, the search for dark matter and the search for extraterrestrial technology merge into a single program. Monitor the solar system for anomalous objects, track their trajectories, analyze their compositions, measure their behaviors. Some will be natural, comets, asteroids, interstellar rocks, but some might be something else. 3I Atlas, whether natural or artificial, is a reminder that the universe has categories we haven't catalogued yet. And the dark matter null results are a reminder that our best theories can be wrong or incomplete, or missing entire dimensions of reality. Both push us to be humble, to stay curious, to question our assumptions. The lesson is clear. When experiments fail to find what they're looking for, it's not just a disappointment, it's information. It's telling you that reality is different from your model. And that's when science gets interesting. That's when breakthroughs happen. Not when experiments confirm expectations, but when they confound them, when the universe refuses to fit the boxes we've built for it. 3I Atlas is doing that for cometary science. The dark matter null results are doing that for particle physics. Both are forcing their respective fields to reconsider, to expand, to think beyond the comfortable frameworks that have worked for decades. And both remind us that the universe is under no obligation to make sense to us. It just is. Our job is to observe, to measure, to theorize, and to revise when the data demands it. And while we're questioning assumptions, let's talk about a technology that used to be science fiction and is now science fact, laser-pushed spacecraft. Part 14, the 2025 Quantum Optics Acceleration Experiment, Laser-Pushed Microcraft. In 2025, a lab demonstrated something remarkable. They accelerated a tiny spacecraft, really just a lightweight sail, a few grams of reflective material using a powerful laser. The photons from the laser hit the sail, transferred momentum and pushed it. Not fast by everyday standards, but fast by space standards. In theory, if you scale up the laser power and optimize the sail, you could push a microcraft to a significant fraction of light speed, maybe 10 or 20% the speed of light, enough to reach nearby stars in decades instead of millennia. This is the breakthrough technology behind projects like Breakthrough Starshot, which aims to send tiny probes to Alpha Centauri, our nearest stellar neighbour, using ground-based lasers to accelerate them. The physics works. Photons carry momentum. A powerful enough laser, focused tightly enough, can impart significant thrust to a lightweight object. No propellant needed, no fuel, just light. The elegance of this approach is hard to overstate. Traditional rockets are limited by the tyranny of the rocket equation. You need fuel to accelerate, but that fuel has mass, so you need more fuel to accelerate the fuel, and so on. It's exponential. To reach even a fraction of light speed with conventional propulsion, you'd need a spacecraft that's mostly fuel tank, with the payload being a tiny fraction of the total mass. Chemical rockets max out at a few kilometers per second. Ion drives can do better, maybe tens of kilometers per second, but they're still nowhere near the speeds needed for practical interstellar travel. Light sails bypass this entirely. The propulsion system stays at home, a massive laser array on Earth or in orbit. The Spacecraft itself carries no fuel. It's just a sail and a minimal payload. The lighter you make it, the faster it can go. Current designs envision sails made of ultra-thin materials, graphene, metallic films, advanced polymers, just a few atoms thick, weighing grams or less. Attach a tiny chip with sensors, communication equipment, maybe a camera, and you've got an interstellar probe that can be accelerated to relativistic speeds without carrying a drop of propellant. The 2025 experiments proved the concept at small scale. Labs managed to accelerate gram-scale test sails to velocities that, if sustained and scaled up, would translate to interstellar-capable speeds. The challenges are immense, keeping the laser focused over vast distances, preventing the sail from tearing or tumbling, protecting the electronics from radiation and impacts during the journey. But the fundamental physics is sound. Light pressure works, laser propulsion works. We're not talking about science fiction anymore. We're talking about engineering problems. Now connect this to 3i ATLAS. If advanced civilizations exist and they want to explore the galaxy, light sails are a plausible way to do it. Send out swarms of tiny probes, each one a lightweight sail attached to a minimal instrument package. Accelerate them with lasers or other directed energy sources. Let them coast through interstellar space for thousands of years. When they approach a star, they can use solar radiation pressure or a small onboard propulsion system to adjust course, slow down, or maneuver. Think about the economics and logistics. With traditional propulsion, each interstellar mission is a massive investment, huge spacecraft, vast fuel reserves, decades or centuries of development. With light sails, you can mass-produce probes, thousands of them, millions even, launch them in waves. Most will fail, collisions with interstellar dust, equipment failures, navigation errors, but some will succeed. It's a numbers game. Send out enough probes, and statistically, some will reach their targets, gather data, and maybe even send back reports. This is how you explore a galaxy if you're patient and methodical. Not one grand mission to one star, but a distributed network of tiny explorers fanning out across hundreds or thousands of light years. Some civilizations might have been doing this for millions of years. Their galaxy could be saturated with these probes, ancient, drifting, most of them dead or dormant, but a few still operational, still executing their programming, still adjusting their trajectories as they encounter new stellar systems. If 3i ATLAS is one of these probes, the 16-hour pulse could be related to stabilization or attitude control. Light sails are inherently unstable. Small perturbations in the sail orientation can cause it to tumble or drift off course. To stay on target, you need periodic corrections, thrusters, or vents, firing at regular intervals to keep the sail oriented correctly. The pulse we're seeing could be those correction burns. Consider the mechanics. A light sail needs to maintain a specific orientation relative to the star it's approaching or departing. If it tumbles, the radiation pressure hits it unevenly, creating torques that can send it spinning wildly. To prevent this, you need attitude control, small thrusters, reaction wheels, or gas vents that can apply corrective forces. If these corrections happen on a schedule, maybe every 16 hours to allow time for navigation calculations, sensor updates, or thermal cycling, you'd see periodic activity. Periodic brightness changes as the vents fire and create temporary plumes of gas or dust. The anti-tail fits too. If the probe is slowing down, it needs to fire thrusters opposite to its velocity vector, sunward if it's moving away from the sun, or in whatever direction opposes its motion. A sunward thrust creates a plume that looks like an anti-tail. Simple orbital mechanics. And here's where it gets interesting. 3i ATLAS is moving at interstellar speeds, tens of kilometers per second. If it wanted to linger in our solar system to study us, to adjust its trajectory for a closer look at Earth or another planet, it would need to decelerate. A light sail can't brake itself. Once you're up to speed, there's no reverse thrust from the original laser back home. You'd need an onboard propulsion system. Small, efficient, capable of repeated firings. The 16-hour cycle could be exactly that. Periodic braking burns, each one designed to shave off a bit of velocity, each one creating a sunward plume as the exhaust reflects sunlight. And the nickel signature? Maybe the probe is encased in a protective shell, metal, ice, or composite material to survive the interstellar journey. As it approaches the sun and heats up, some of that shell ablates or vents, releasing metal particles into the coma. Not because the probe is made of nickel, but because nickel is part of the shielding. Interstellar space is hostile. You've got cosmic rays, high-energy particles that can damage electronics and erode materials. You've got micrometeorites, tiny grains of dust moving at relative velocities of hundreds of kilometers per second, each one a potential projectile. You've got temperature extremes near absolute zero in the void, searing heat when you approach a star. A probe designed to survive this needs protection. A thick shell of ice, accreted from interstellar hydrogen and dust over millennia, would work. Ice is abundant, it's a good radiation shield, and it sublimates harmlessly as you approach a star. But underneath the ice, you'd want a harder shell, metal, ceramic, composite, to protect the delicate instruments inside. If 3i ATLAS has such a shell, and if that shell contains nickel or nickel alloys, then as the outer ice layer sublimates and the inner shell heats up, small amounts of metal could ablate or be mechanically ejected, maybe from the same vents used for attitude control. You'd see metallic signatures in the coma mixed with the gas and dust. Not a lot, just traces. But enough to detect with sensitive spectroscopy. This isn't proof. It's a framework, a model that fits the observations. But it's a model based on technology we're developing right now. Light sails aren't alien magic, they're physics. And if we're building them in 2025, it's not unreasonable to think another civilization, with a few thousand or million years head start, built them long ago and sent them out. The implications are staggering. If light sail probes are feasible, and if civilizations tend to send them out, then the galaxy could be full of them. Millions, billions of tiny spacecraft drifting between stars, most of them dark and inactive, a few of them lighting up when they pass close to a star. We'd only detect the ones that happen to pass through our solar system and happen to be active. The rest would be invisible, contributing to the dark matter budget or just ignored as noise in surveys. This reframes the search for extraterrestrial intelligence. We've been listening for radio signals, looking for megastructures, scanning for technosignatures in exoplanet atmospheres. Maybe we should also be watching for weird objects in our own backyard. Small, fast, pulsing, with jets and anti-tails and periodic brightness variations. Because if light sail probes exist, 3i ATLAS could be the first one we've recognised, and if it is, others will follow. The search strategy changes completely. Instead of pointing radio telescopes at distant stars hoping to catch a deliberate transmission, we'd monitor nearby space for anomalous objects. Things that move wrong, brighten wrong, behave wrong. We'd catalogue them, track them, analyse their trajectories and compositions. We'd look for patterns. Do they cluster in certain orbits? Do they favour certain stellar types? Do multiple objects share similar characteristics, suggesting a common origin? And we'd build better detection systems. Current surveys catch the brightest, closest objects. But if most light sail probes are small and dark, we're missing the majority. We need more sensitive instruments, wider coverage, longer integration times. We need AI pipelines trained specifically to recognise artificial signatures, periodic pulses, trajectory adjustments, spectral anomalies that don't match natural objects. But even if 3i ATLAS is natural, the light sail experiments are a reminder that interstellar travel, at least for small probes, is within reach. Not now, but soon. In our lifetime, we might send our own probes to other stars, and when we do, they'll look a lot like 3i ATLAS. Small, fast, possibly encased in protective ice, pulsing periodically as they adjust course. And maybe, in some distant solar system, another civilization will look up, see our probe, and wonder, is that natural or artificial? That's the mirror. Moment. The realization that if we're building interstellar probes, someone else probably has too. And if our probes look like 3i ATLAS, then 3i ATLAS might be someone else's probe looking back at us. Its symmetry, its inevitability. If physics allows it, and if intelligence is common enough, then the galaxy should be full of these things. We're just now reaching the technological level to recognise them, and 3i ATLAS might be the first hello. Which brings us to the final piece. The broader pattern of unexplained signals that 2025 has delivered. Part 15. The broader lens. A quiet but growing pattern of unclassifiable transients. 2025 has been a year of anomalies. 3i ATLAS pulsing like a heartbeat. Neutrino bursts from the galactic centre. Null results from dark matter experiments. Laser-pushed microcraft proving interstellar travel is plausible. But those are just the headlines. Dig deeper, and you'll find a quiet accumulation of smaller signals, transients, oddities that don't quite fit. There are optical transients, flashes of light in the sky, lasting seconds to hours, that don't match known categories. Not supernovae, too fast. Not variable stars, wrong spectrum. Not gamma-ray bursts, wrong energy. Just flashes. Detected by automated surveys, flagged by AI, catalogued as unclassified transient event, a few per month. Most ignored because there are so many, and follow-up telescope time is limited. These optical transients are haunting in their mystery. They appear without warning, brighten to detectable levels, then fade back into darkness before anyone can point a major telescope at them for follow-up spectroscopy. By the time the alert goes out and observation proposals get written and scheduled, the event is over. We're left with a handful of data points, position, brightness curve, maybe crude colour information, and a label that essentially means we don't know what this was. Some might be distant supernovae caught at unusual phases, some might be flare stars we haven't catalogued yet, some might be asteroids tumbling in just the right way to create brightness spikes. But the sheer variety is unsettling. They don't cluster into neat subcategories. Each one seems unique, or nearly so. And the AI systems flagging them don't care about our desire for patterns. They just report this thing brightened unexpectedly. Here's the data, figure it out. There are radio microbursts. Fast radio bursts get the press. Those millisecond duration pulses from distant galaxies that no one fully understands. But there are also slower, fainter radio signals, detected in archival data from surveys that weren't even looking for them. Repeating sometimes, non-repeating other times. Too faint to localize precisely. Too weird to dismiss as interference. Radio astronomy generates enormous data sets. Surveys scan the sky continuously, recording everything above a certain sensitivity threshold. Most of it is mundane, pulses we've known about for decades, distant galaxies emitting steady synchrotron radiation, interference from satellites and terrestrial sources. But buried in the archives are these odd signals, not loud enough to trigger automatic alerts, not obvious enough to catch a human observer's eye during initial data reduction. But when you go back later, when you apply more sophisticated algorithms or when you're specifically hunting for anomalies, they're there. Some repeat with irregular intervals, days, weeks, months between events. The repetition suggests a natural source, some kind of periodic or quasi-periodic astrophysical process. But what process? Pulsars are far more regular. Flare stars operate on different timescales. Accretion events around black holes or neutron stars could work, but the emission properties don't quite match. So they sit in the pending category, waiting for more data, waiting for someone to develop a model that explains them. Others don't repeat at all, or at least haven't been seen to repeat yet. Single events, possibly one-off cataclysms, possibly the first detection of something that happens regularly but rarely. Without repetition, there's no way to predict when to look next, no way to coordinate multi-wavelength observations. These are the most frustrating, tantalizing hints of something interesting, but no path forward to understand them better. There are exoplanet atmospheric anomalies. Spectroscopy of exoplanet atmospheres sometimes shows unexpected absorption lines, molecules or elements that shouldn't be there, or in abundances that don't match models. Most are explained away as calibration errors or contamination from the host star. But some linger, unexplained, in the needs follow-up pile. Exoplanet atmosphere studies are at the cutting edge of observational astronomy. When a planet transits its star, starlight passes through the thin shell of the planet's atmosphere. Molecules in that atmosphere absorb specific wavelengths, creating absorption lines in the spectrum. By analysing those lines, we can determine composition, water vapour, methane, carbon dioxide, even more exotic molecules. The technique is incredibly sensitive, which means it's also vulnerable to systematic errors. Instrumental noise, stellar activity, data processing artifacts, all of these can create false signals that look like atmospheric features. Most anomalies turn out to be exactly that, artifacts. But not all of them. Some planets show absorption features that persist across multiple observations, that survive rigorous error analysis, that just don't match what planetary formation and evolution models predict. Maybe there's water vapour on a planet that should be too hot for water to exist. Maybe there are organic molecules in abundances that suggest active chemistry. possibly even biological processes. Maybe there are elements that shouldn't be present unless something very unusual happened during planet formation. These aren't smoking guns for extraterrestrial life or weird physics, they're just odd. And until we get better data, higher resolution spectra, or develop more sophisticated atmospheric models, they remain in limbo. There are gamma-ray oddities, X-ray flickers, infrared spikes. The universe is noisy, and most of that noise is natural. But when you start aggregating the anomalies, when you look at the full catalogue of things we don't understand, a pattern emerges. Not a conspiracy, not a hidden structure. Just a realization our frameworks are being stressed. Gamma-ray telescopes detect the highest energy photons in the universe, typically produced by the most violent events, supernova, black hole jets, neutron star collisions. But occasionally they catch something brief and energetic that doesn't match any known source. An unidentified burst from a seemingly empty patch of sky. A flicker from a galaxy that shows no other signs of activity. These get catalogued, cross-referenced with other wavelengths to see if there's a counterpart in optical or radio, and usually shelved when nothing conclusive emerges. X-ray astronomy faces similar challenges. X-rays come from hot gas, from matter falling into compact objects, from stellar coronae. The sources are well understood, mostly. But the archives are full of transient X-ray sources that appeared once and never again, or flickering sources with irregular timing that don't match known pulsars or binaries. Each one is a puzzle piece that doesn't fit anywhere in the current picture. Infrared astronomy detects heat, which means it sees things that are warm but not hot enough to glow in visible light. Brown dwarfs, dust clouds, distant galaxies obscured by dust, even planets around other stars. But infrared surveys also pick up transients, brief brightenings that suggest sudden heating, possibly from impacts, possibly from eruptions, possibly from something else. Without follow-up, without knowing what the object is or where it went after the event, interpretation is guesswork. The better our instruments get, the more anomalies we find. This isn't surprising, it's expected. As sensitivity improves, you start seeing things that were below the noise floor before. As coverage expands, you catch rare events that only happen occasionally. As AI takes over, you stop filtering data through human preconceptions and start seeing everything, including the stuff that doesn't fit. This is a crucial point. Human observers, even trained astronomers, bring biases to data analysis. We look for things we expect to see. We have mental models of what stars, galaxies, transients should look like, and we filter observations through those models. Things that don't fit get dismissed as noise, artifacts, or check this later cases that never get checked. AI doesn't have those biases, or rather, it has different biases, based on how it was trained. An AI trained to detect anything unusual will flag unusual things, even if they don't match human expectations. This is both a blessing and a curse. More discoveries, but also more noise, more false positives, more "what the hell is this" moments. 3i ATLAS is part of this broader trend. It's an object that doesn't fit the Comet box, the asteroid box, the interstellar visitor box, or the probe box. It's something else. Maybe it's a new class, maybe it's a hybrid, maybe it's just weird, a one-off statistical fluke that we happen to catch. But it's not alone. It's one of many signals pushing at the edges of our categories, asking us to expand our thinking. The philosophical question is, what happens when data refuses to fit? When your taxonomy breaks down? When comet and asteroid and planet and star and galaxy aren't enough? You have two choices. Force the data into existing boxes, stretching definitions until they're meaningless, or create new boxes, new categories, new frameworks that accommodate the weird stuff. History suggests the second approach is more productive, though also more painful. Every major advance in astronomy has involved recognizing that the old categories were insufficient. Before the 20th century, nebulae were just fuzzy patches in the sky, maybe gas clouds, maybe unresolved star clusters. Then Edwin Hubble showed that some nebulae were actually entire galaxies, island universes as vast as our own Milky Way. The category nebula split into multiple categories: emission nebulae, reflection nebulae, planetary nebulae, galaxies, each with distinct physical properties, distinct formation mechanisms, distinct evolutionary paths. Science has done this before. Quasars didn't fit any known category when they were discovered. Too bright, too small, wrong spectrum. So we created a new category. Pulsars, same thing. Gamma ray bursts, fast radio bursts, exoplanets, dark energy. All of these were anomalies first, then categories later. 3i ATLAS might be the start of a new category, or it might remain an outlier. But either way, it's teaching us something. The process is messy. Early observations of pulsars were so bizarre, perfectly regular radio pulses repeating like clockwork, that some astronomers half-seriously wondered if they were artificial signals, beacons from extraterrestrial civilizations. They even labelled the first one LGM1 for Little Green Men. Only after more pulsars were discovered, after theoretical work showed that rotating neutron stars could produce exactly such signals, did the natural explanation win out. But the initial weirdness, the refusal of the data to fit existing categories, was necessary. It forced astronomers to think harder, to develop new models, to expand their understanding of what neutron stars could do. 3i ATLAS is in that same uncomfortable zone. The data is weird, the models don't fit. We're forced to speculate, to propose new mechanisms, maybe even to consider possibilities that sound outlandish. That's okay. That's how science progresses. You propose, you test, you refine. Most speculative ideas turn out to be wrong, but some don't. And even the wrong ideas teach you something, because figuring out why they're wrong often reveals new aspects of the underlying physics. And here's the hopeful part. The universe is big, really big, and we're just starting to see it properly. For most of human history, we saw the sky with naked eyes, stars, planets, maybe a comet if we were lucky, then telescopes, then photography, then digital imaging, then space telescopes, then AI-driven surveys. Every step we see more. Every step we find things we didn't expect. The pace of discovery is accelerating. In the past decade alone, we've confirmed thousands of exoplanets, detected gravitational waves, imaged a black hole's event horizon, discovered fast radio bursts, tracked interstellar visitors through our solar system. Each of these was impossible or purely theoretical a generation ago. Now they're routine observations, catalogue entries, data points for statistical studies. What will the next decade bring? What will we see when the next generation of telescopes comes online? More sensitive, wider fields of view, better spectral resolution, continuous monitoring across all wavelengths. How many more 3i ATLAS-like objects will we find? How many anomalies will graduate from weird outlier to new category with dozens of examples? 3i ATLAS is a reminder that the universe still has surprises, that despite all our knowledge, all our models, all our confident predictions, there are things out there that don't play by our rules. And that's exciting. That's what drives science, the hunt for the unexpected, the pursuit of the anomaly, the thrill of finding something that makes you question everything. So keep watching the skies, keep demanding more data, keep thinking beyond the labels, because whether 3i ATLAS is a comet, a probe, or something entirely new, it's proof that we don't have it all figured out. The universe is bigger, stranger, and more interesting than we imagined. And somewhere, right now, another anomaly is pulsing, blinking, or whispering across the void, waiting for us to notice. The heartbeat continues, 16.16 hours. Again, and again, and again. And until we have the full story, until someone releases that smoking gun time-lapse, until we get spectroscopy that confirms or denies the heavy metals, until we catch the jets in the act and measure their alignment, we're left with the most human of all scientific states, wonder, uncertainty, and the nagging suspicion that we're looking at something profound, something that, once understood, will change how we see the cosmos, or maybe how the cosmos sees us. This is the frontier, not some distant galaxy or exotic quantum realm, but right here, in our solar system, drifting past us at interstellar speeds, an object that refuses to be understood, that challenges every assumption that might be natural or might be something else entirely. We're watching it in real time, gathering data, running analyses, debating interpretations, and every 16.16 hours it pulses again, reminding us that it's still there, still active, still waiting for us to figure it out. Either way, the pulse keeps beating, and we keep watching.